First light, the birth of stars and galaxies. The James Webb. Space Telescope's very first deep-field image, released in July 2022, compressed 13.1 billion years of cosmic history into a single mosaic. Thousands of galaxies, some smaller than a grain of sand held at arm's length, glowed in infrared light. Many of them formed only 200 million years after the Big Bang. For astronomers, it was not just a photograph, it was a revelation. Prior to Webb, Hubble had already stretched human vision into the early universe, showing galaxies as they appeared 400 to 500 million years after cosmic dawn. But Webb's infrared sensitivity, extending to 28 microns with the mid-infrared instrument, MIRI, smashed through that barrier. Suddenly, impossible galaxies emerged. Mature, massive structures that should not have existed so soon after the Big Bang. The cosmic evolution. Early release science, Keir's survey, confirmed objects with stellar masses equivalent to billions of suns at redshifts of Z 10 to 13, corresponding to just 250 million years after the universe's birth. This contradicted established lambda cold dark matter cosmological models. Galaxy formation, according to decades of simulations, should have been slow and hierarchical, small clumps merging over hundreds of millions of years. Yet Webb's data suggested that some galaxies formed at 10 times the expected pace, forcing astrophysicists to revisit the very parameters of early star formation and dark matter dynamics. Beyond galaxies, Webb opened stellar nurseries to infrared vision. In the Carina Nebula, a turbulent star-forming region 7,600 light-years away, it resolved protostars in exquisite detail. Jets of ionized gas speared into the surrounding interstellar medium, while dense cocoons of molecular hydrogen, previously opaque to Hubble, revealed nascent stars still accreting material. A LMA, Atacama Large Millimeter Submillimeter Array, in Chile, added complementary data. Radio maps of cold dust and gas feeding those stars. Together, Webb and ALMA painted a complete picture of stellar genesis, radiation pressure, turbulence, and magnetic fields woven into cosmic architecture. Meanwhile, Gaia's third data release, 2022, revolutionized our understanding of the Milky Way's structure. By precisely measuring the parallax of over 1.8 billion stars, Gaia revealed ripples in our galaxy's disk, remnants of ancient collisions with the Sagittarius dwarf galaxy. The data even captured the Milky Way's bar-like core and ongoing stellar migration, showing how galactic structure is dynamic and evolving, not static. Every new dataset raised sharper questions. Were the earliest galaxies growing by unusually efficient star formation, or is our cosmological model missing fundamental physics? Could exotic forms of dark matter, self-interacting warm rather than cold, explain the accelerated build-up? These are not minor adjustments. They cut to the very framework of modern cosmology. The James Webb Space Telescope's first deep field did more than impress. It detonated expectations. In a single composite of SMA CS0723, released on 11 to 12 July 2022, thousands of galaxies, some magnified and stretched into luminous arcs by the cluster's gravity, appeared at once, with the faintest object shining, from a time only a few 100 million years after the Big Bang. That image, taken with NARCam and refined with NARSPEC spectra, signaled that the 21st century's great leap in cosmology had truly begun. Not a better version of what Hubble already did, but an entirely new band of reality, dust-piercing infrared, where first-generation galaxies, buried in redshift, finally step into view. NASA Webb Telescope. In the months that followed, early Webb programs, JADES, SEERS, GLASS, Cosmos Webb, pushed to higher redshift candidates, and then hard-won spectroscopic confirmations. The JADES team, combining deep NIRCam imaging with NIRSpec, multi-object spectra, nailed down galaxies at Z greater than or equal to 12 to 13. Light left them when the universe was less than 330 million years old. Those redshifts are not press release exuberance. They're locked by clean Lyman breaks and nebular line placements in the spectra. Even if the absolute record holder shuffles as new measurements come in, the critical fact stands: luminous, compact systems existed astonishingly early, with stellar masses and star formation rates that strain the comfortable timelines of hierarchical growth. esaweb.org. Why is this shocking? In lambda-cold dark matter, gravity builds structure from the bottom up. Small halos merge to make bigger ones. Star formation ramps as metals and dust build up, and feedback from supernovae and young stars regulates growth. You can get bright galaxies early, but not too bright, and not too many. Yet Webb's tallies suggest a population of surprisingly luminous, relatively mature systems within the first few 100 million years. Cosmologists have responded on two fronts. One is conservative. Maybe star formation in the earliest halos is far more efficient than in the local universe. Perhaps the initial mass function International Monetary Fund was top-heavy, producing more massive, short-lived stars that boost luminosity per unit mass. Perhaps dust forms ultra-fast in pair instability supernovae, altering colours and inferred ages. The other front is more radical. Maybe our assumptions about dark matter microphysics, feedback coupling, or the ionizing background need revision. Webb also turned the floodlights on nearby stellar nurseries, providing a physical counterpoint to those cosmological puzzles. In Carina, the Pillars of Creation and the Tarantula Nebula's R136 region, NIRCam and MIRI resolved protostars still accreting through dusty envelopes and protoplanetary disks. Jets carve cavities. Ultraviolet radiation from O-type giants sculpts elephant trunks of cold gas, and complex hydrocarbons fluoresce along photodissociation fronts. The science is not just pretty pictures. Accretion rates, outflow momenta, ionization fronts, and dust grain size distributions can now be measured in the same structures where stellar seeds are growing, letting us tie microphysics, ambipolar diffusion, radiation pressure, magnetohydrodynamic turbulence, to macroscopic outcomes, cluster mass functions, triggered star formation. Put bluntly, if you want to understand why galaxies grow the way they do, you must get star formation right in environments both local and primordial. And Webb, for the first time, can measure the obscured stages systematically, rather than infer them indirectly. ALMA, sitting 5,000 meters up on the Chajnantor Plateau, completes the picture by tracing the cold universe. With baselines stretching up to 16 kilometers, ALMA resolves sub-O structures in nearby disks and sub-kiloparsec molecular complexes in high-Z galaxies. Its public unveiling of H.L. Tau's disk in 2014, with razor-sharp rings and gaps, shocked theorists. A million-year-old system already showed architecture suggestive of planet-disk interactions. That one image propelled a decade of new models in which pebble accretion, pressure bumps, and early dust growth conspire to build planets far faster than classical core accretion timescales allowed. ALMA's chemistry adds another layer. Detections of CO isotopologues, HCN, H2_22CO, and more recently, water vapor in the inner astronomical units, constrain the temperature and volatility gradients that set where rocky, icy, and gaseous worlds can form. The implication for galaxies is profound. If planets assemble early and efficiently in typical disks, then metal and dust cycles in star-forming regions are more dynamic than previously assumed, feeding back into infrared luminosities and gas depletion times that we measure on galactic scales. ALMA Observatory Wikipedia. Gaia, meanwhile, rewires our understanding of this galaxy, the stage on which all our local star formation plays out. With DR3, the mission provided positions, parallaxes, proper motions, and photometry for approximately 1.8 billion sources, turning the Milky Way from a static picture into a kinematic movie. The disk ripples, the bar breathes, tidal streams, Gaia Enceladus, the Sagittarius dwarf debris, the Helmi stream, crisscross the halo. These structures are not trivia. They encode the merger history that set our star formation rate, chemical evolution, and even the distribution of dark matter substructure. When cosmological simulations try to reproduce Milky Way analogues, they now have to pass the Gaia test. Do the orbits, ages, and metallicities of stars line up with the specific collisions our galaxy suffered? Only then can we trust them to extrapolate back to the high Z conditions Webb is revealing. Cosmos ESA Science. Let's thread these instruments into a single data-driven narrative. Imagine a high redshift galaxy in the reionization era at Z approximately 10 to 13. Its stellar mass is 10 to the power of 8, 10 to the power of 8 to 10 to the power of 9, M10 to the power of 9m. Its half-light radius a few hundred parsecs, and its specific star formation rate tens per year. The UV slope is blue, implying low dust, yet nebula lines infer metallicities already at a few percent solar. Where did those metals come from so fast? A plausible path is a bursty formation mode with short free fall times in dense, low angular momentum gas clumps, seeded by population, 3 supernovae, and rapidly enriched by a top-heavy IMF. If such a galaxy sits in a favorable lensing configuration behind a cluster, SMA CS07, 23 is a template. Magnification boosts both detectability and spatial resolution, letting NearSpec pull out O3 and H-beta lines to pin the redshift. Meanwhile, ALMA can chase C2 158 micrometers or O3 88 micrometers lines, brilliant coolants in early systems, to constrain gas kinematics and dynamical mass, testing whether the stellar masses inferred from SED fits are overestimated or not. If dynamical masses come in below stellar mass estimates, you've got template mismatch or IMF issues. If they're higher, unseen gas and dark matter might be dominating. That cross-check, JWST stars versus ALMA gas, has become the gold standard for turning pretty early galaxy into a physical system with tensions you can quantify. Back in the nearby universe, Webb's dissection of the Tarantula Nebula, 30 Doradus, provides a high-signal laboratory for cluster formation in conditions that echo early galaxies: low metallicity, intense radiation fields, and enormous surface densities. R136, its core cluster, hosts some of the most massive stars known. By measuring the luminosity function of young stellar objects across the nebula and mapping PAH emission, Webb constrains how the IMF varies, or stubbornly doesn't, with environment. If the IMF tilts to high masses in starbursts, early galaxies can turn gas into UV luminosity extraordinarily efficiently. Exactly what the AZ greater than 10 counts seem to be telling us. Conversely, if the IMF is stubbornly universal, then only very high gas accretion rates or reduced feedback can explain early brightness. Either way, the diagnostics Webb supplies, nebula line ratios, dust continuum slopes, resolved protostar demographics, are the numbers modelers must hit. ALMA's high Z contributions go beyond molecules. By detecting C2 and dust continuum in Z, greater than 6 systems, it measures the far infrared luminosity, and hence the obscured star formation rate. often the dominant piece missing from UV-based SFRs. A pattern has emerged. Some early galaxies are dustier than expected, while others are almost dust-free. That diversity is a feature, not a bug. Dust production channels, core collapse SNE, AGB stars, grain, growth in the ISM, have different timescales. ALMA's continuum slope plus line ratios let us differentiate them. In some Z7 galaxies, C2 is surprisingly weak compared to SFR, pointing to low carbon abundance or high ionization parameters. In others, C2 is bright but dynamically cold, implying ordered rotation already in place. Those details feed back into the question of how quickly disks settle in a young universe, and whether mergers or smooth cold flows dominate mass assembly. GAIA closes the loop by anchoring star formation recipes locally. Starquakes, astroseismology. In DR3, tightened stellar age scales. Kinematics pinpointed moving groups and expanding shells from long-dead clusters. And precise distances recalibrated the luminosities of standard candles. Cosmology is downstream of all that. When you adopt a star formation law in a simulation, you're implicitly trusting Gaia-calibrated physics. When you infer a star formation rate from a UV slope at Z equals 12, you're extrapolating those calibrations into a regime Webb now shows is more diverse than textbook plots imply. That is the subtle power of 21st century synergy. Datasets that look unrelated, parallaxes in the solar neighborhood versus nebula lines in the first galaxies, become the two ends of a single lever that can pry open the physics of how the universe lit up. Cosmos. Finally, step back and look at the meta-trend. Astronomy used to be a one-messenger science dominated by photons in a narrow band, with theory filling in the rest. Today, the instrumentation stack is broad and deliberately overlapping. Webb resolves dusty birthplaces. ALMA weighs cold gas and dust and times chemistry. Gaia turns our galaxy into a dynamical textbook. Ground-based 8 to 10 meter class telescopes feed medium and high-resolution spectra. And soon, the Nancy Grace Roman Space Telescope and the extremely large telescope will add wide-field deep imaging and diffraction-limited spectroscopy from the ground, while Euclid maps weak lensing to trace dark, matter scaffolding across cosmic time. The point is not that everything is solved, it's that constraints are now tight enough to falsify complacent stories. If early galaxy masses or number densities remain too high, after spectroscopic vetting, feedback prescriptions and even dark matter models will have to move. If they don't, then the lesson is that nature can assemble stars with brutal efficiency when conditions allow. And the first billion years were exactly such a furnace. The story of the first stars and galaxies cannot be separated from the universe's great transition. Reionization. After recombination at approximately 380,000 years, hydrogen atoms filled the cosmos, and the universe went dark, except for the faint afterglow of the cosmic microwave background. The dark ages stretched until the first stars ignited, and their UV radiation began ionizing neutral hydrogen, punching holes of transparency into the cosmic fog. Webb has sharpened the timeline. Spectroscopic confirmation of galaxies at Z, greater than 10, provides direct probes of ionizing emissivity. By measuring Lyman alpha damping and the Gunn-Peterson trough in high Z quasar spectra, astronomers constrain the fraction of neutral hydrogen in the intergalactic medium, IgM. Webb's NIRSPEC now allows faint galaxies, not just quasars, to be used as beacons. Early results suggest that reionization was well underway, by Z approximately 8, and possibly patchy even earlier. Ground-based instruments like VLTX Shooter and Keck's Mossfire add complementary data, but Webb's sensitivity enables line detections that were impossible before. Meanwhile, 21-centimeter cosmology, LOFAR, HERA, and the upcoming SKA, seeks the direct neutral hydrogen signal of reionization, providing the large-scale map to match Webb's zoomed-in galaxies. This dual-front approach, infrared photons plus radio waves, will close one of the last gaps in our cosmic timeline. When exactly did first light transform the universe from neutral to ionized? The role of feedback in early galaxy growth. The existence of bright galaxies so early raises a thorny question. How did they avoid being throttled by feedback? In local galaxies, star formation is self-regulated. Intense starbursts produce winds, supernovae, and radiation pressure that eject gas and shut down further growth. Yet Webb is finding galaxies that formed stars with extreme efficiency, apparently without collapsing under their own feedback. One possibility is that early halos had much higher gas fractions, 70 to 90%, compared to 10 to 20% in modern galaxies. With such deep reservoirs, feedback may stir turbulence, but not eject mass. Another is that supernovae were less effective in low metallicity environments, allowing gas to cool and fall back quickly. Cosmological simulations like FIRE2 and Illustri's TNG, when adjusted with Webb constraints, are now testing these mechanisms. ALMA, by tracing molecular gas and outflows in high-Z galaxies, provides the missing check. Is feedback actually weaker, or are we catching galaxies in brief, intense phases before blowout occurs? Population 3 stars. The first giants. At the very dawn of star formation, before any metals existed, the first stars, population 3, burned hydrogen and helium only. These giants, predicted to be 100 to 300 solar masses, lived for just a few million years before exploding as pair instability supernovae, seeding the cosmos with the first carbon, oxygen, and iron. For decades, population 3 remained hypothetical. Now, Webb offers indirect glimpses. Spectra of galaxies at Z greater than 10 sometimes show unusually strong helium lines or weak metal lines, potential fingerprints of POP3 clusters. ALMA's non-detections of certain fine structure lines in these systems bolster the idea. Future JWST ultra-deep programs may catch direct POP3 supernovae as transients, brief flashes from the true first stars. If confirmed, it would complete a story that began with theory in the 1960s and culminates in direct observation in the 2020s. Supermassive black holes at dawn. The detection of luminous quasars at Z approximately 6 to 7 already implied that black holes of 1 billion solar masses existed within the first 700 million years. Webb is now extending this puzzle to even higher redshifts. How do you grow such monsters so fast? Two pathways dominate the debate. Light seeds, collapse of massive POP, 3 stars, requiring rapid, nearly uninterrupted Eddington accretion. Heavy seeds, direct collapse of pristine gas clouds into 105 solar masses, black holes, needing special conditions like strong Lyman-Werner radiation fields. NIR spectra from Webb hint at faint AGN activity in some Z greater than 7 galaxies, suggesting that black holes and galaxies co-evolved almost from the start. The Event Horizon Telescope, by imaging M87 star and Sagittarius A star, anchors the physics of black hole horizons today. LIGO Virgo's black hole merger demographics map, intermediate mass black holes, and Webb connects these to their earliest ancestors. Together, they build a cosmic genealogy of black holes across time. Simulations and theory on trial. Perhaps the most exciting aspect of Webb's early results is how mercilessly they stress-test theory. Large-scale simulations like Illustri's TNG, EAGLE, and FIRE were calibrated to Hubble-era data. Within weeks of Webb's first deep fields, theorists scrambled to rerun simulations with altered assumptions, higher star formation efficiency, top-heavy IMFs, or exotic dark matter models, self-interacting or warm. Some simulations with minor tweaks can reproduce the luminous early galaxies. Others fail spectacularly, predicting too few massive halos to host them. This back and forth exemplifies 21st century science. Data drives the models, and models adapt or break. The impossible galaxies are not a crisis. They are the crucible in which cosmology itself is being reforged. The road ahead. Next instruments. Webb is just the first step. Nancy Grace Roman. Space Telescope, 2027. Wide-field infrared surveys to complement Webb's pencil beams. Extremely Large Telescope, Chile, circa 2028. 39-meter aperture. Diffraction-limited AO spectroscopy of early galaxies. SKA, 2030s. Direct 21-centimeter maps of reionization. Euclid. Launched 2023. Dark matter scaffolding via weak lensing. The dawn of galaxies will not remain a mystery for long. By 2035, astronomers expect a coherent, multi-wavelength, multi-messenger map of how the first billion years unfolded. Reionization simulations and the patchy universe. The epoch of reionization wasn't a neat, uniform switch. It was patchy, like a fog burned away by scattered campfires. Galaxies, star clusters, and early quasars ionized bubbles of hydrogen around them, and these bubbles eventually overlapped into transparency. Modern simulations, from the Renaissance Project to THESN, a cosmological radiation hydrodynamics code built on Arapo, recreate this messy cosmic dawn in unprecedented detail. THESN, run on supercomputers like Super-M UCNG, integrates radiation transfer with galaxy formation physics. Its outputs are eerily close to what Webb is now finding. Tiny galaxies driving most of the ionizing photon budget, with occasional quasars carving larger holes. Webb's discovery of faint galaxies with steep UV luminosity functions at Z, greater than 8, strengthens this idea. That the universe's transparency was achieved by the many, not the few. Radio telescopes are the other half of this story. HERA, Hydrogen Epoch of Reionization Array. In South Africa, has placed upper limits on the 21-centimeter signal, and the Square Kilometre Array, SKA, when complete, should directly image those ionized bubbles. Pairing Webb's pinpoint galaxies with SKA's wide-field hydrogen maps will, for the first time, allow astronomers to say exactly which galaxies reionize the universe, and when. Chemical evolution in the first galaxies. Stars don't just shine, they forge elements. Every detection of oxygen, carbon, or iron in early galaxies tells us something about how quickly the cosmos enriched itself. Webb's Aniaspec is detecting nebular lines like O3 and H-beta in galaxies less than 400 million years old. In some cases, metallicities already reach a few % of solar, astonishing given the short timescales. This means multiple stellar generations had already lived and died in record time. Pair instability supernovae from massive population 3 stars likely seeded those galaxies with their first metals, while rapid type 2 supernovae from 20 to 50, solar mass stars continued the cycle. ALMA follows up with C2 and O3 fine structure lines in the submillimeter, measuring metallicity, dust, and cooling rates. One puzzle is diversity. Some galaxies at Z, approximately 7 to 8, appear chemically primitive, with extremely low dust and metals, while others already look surprisingly enriched. This unevenness suggests a cosmos where local conditions, halo mass, environment, inflow rates, determined whether enrichment raced ahead or lagged behind. By comparing Webb spectra with simulations, astronomers can now test whether enrichment was driven by isolated bursts or steady, sustained star formation. The dust paradox at cosmic dawn. Dust, those tiny grains of carbon and silicates, is both a nuisance and a key player in cosmic history. It absorbs UV light and re-emits in the infrared, shaping how galaxies appear. For decades, theorists expected that dust formation should lag hundreds of millions of years. Since AGB stars, the factories of carbon dust, take time to evolve. Yet ALMA has repeatedly detected dust in galaxies at Z greater than 7. In some cases, the dust masses rival those in much older systems. The paradox: how did so much dust form so quickly? One answer is that supernovae themselves, not AGB stars, seeded the earliest dust. Observations of SN 1987. And more recent events confirm that supernova ejecta can condense significant amounts of dust, which may survive if shielded in dense clumps. Webb strengthens this picture by measuring the infrared slopes of Z greater than 10 galaxies. Some show clear evidence of dust reddening, even this early. Others remain pristine. The emerging view is that the dust cycle began far earlier and more efficiently than expected, and that dust is not merely an afterthought, but a controlling factor in how galaxies grew luminous. Case study: GNZ 11 and its lessons. One galaxy in particular, GNZ 11, has become a poster child for cosmic dawn. Initially identified by Hubble in 2016 at Z approximately 11.1, it was for years the record holder for most distant known galaxy. Webb has revisited GNZ 11, confirming its extreme distance and revealing far more detail. Spectra show strong O3 emission, indicating active star formation, and hints of unusually high nitrogen abundance, potentially from Wolf-Rayet stars. Even more intriguing, Webb's high resolution suggests compact morphology, a small, intense starburst region, rather than a diffuse system. Why does GNZ 11 matter? It proves that galaxies this luminous exist at an epoch where theory said they should be vanishingly rare. It has forced recalibration of halo mass functions and star formation recipes. GNZ 11 is not unique. JADES and CEERS have found many similar candidates, but as the first, it highlights how even a single outlier can reshape cosmology. Case study: the GLASS Z12 and JADES galaxies. The GLASS survey with Webb reported galaxies at Z, approximately 12, later confirmed by JADES with spectroscopy. These systems, seen just 350 million years after the Big Bang, are compact and surprisingly luminous. Their inferred star formation rates are 5 to 20 solar masses per year. Extraordinary given the youth of the universe. Follow-up with ALMA is already underway to detect C2 lines and test whether these galaxies are dynamically stable or turbulent mergers. If stable, they suggest disk formation occurred far earlier than expected. If turbulent, they reveal that early galaxies were chaotic starburst factories. Either result has profound consequences for models of galaxy assembly. The connection to cosmic large-scale structure. Even at the dawn of galaxies, the cosmic web was already shaping their fate. Simulations show that gas streams along dark matter filaments fed proto-galaxies, igniting bursts of star formation. Webb's wide-area surveys, like Cosmos Webb, covering 0.6 square degrees, are designed to map not just single galaxies, but the environments they lived in. Already, protoclusters have been identified at Z approximately 7 to 10. overdensities of galaxies hinting at the seeds of today's massive clusters. These discoveries confirm that structure formation was hierarchical, but also rapid. Clusters of galaxies were assembling when the universe was still less than 5% of its current age. Looking forward, Webb's next decade. Chapter 1 concludes with Webb's roadmap for the 2000s. Scheduled ultra-deep surveys will push to fainter magnitudes and confirm hundreds of galaxies at Z greater than 10. Combined with ALMA, Gaia, Euclid, and eventually Roman, astronomers will not only count galaxies, but weigh them, map their chemistry, and connect them to the cosmic web. By the end of the decade, the impossible galaxies may either be reconciled with lambda CDM through refined feedback and star formation models, or may force more radical revisions, perhaps to the nature of dark matter itself. What is certain is that the first light is no longer abstract theory. It is a data set, rich and growing, and it is rewriting the opening chapter of cosmic history before our eyes. One of the most striking implications of Webb's early data is that galaxies in the first 500 million years appear to convert their gas into stars with ruthless efficiency. In the modern universe, only a few % of gas in molecular clouds forms stars before feedback halts the process. But spectral energy distributions of high-Z galaxies imply star formation efficiencies of 10 to 20%, perhaps even higher. Why? Part of the answer may be cosmic conditions. Gas fractions in early halos approached 90%, leaving dense reservoirs immune to blowout. Cooling pathways were also more limited, dominated by hydrogen and helium lines rather than metal line emission, forcing clouds to collapse into massive stars rather than fragment into small ones. Webb is measuring Balmer line strengths, UV slopes, and nebula emission to refine these numbers. Meanwhile, ALMA observations of C2 and dust continuum place limits on gas masses, offering an independent handle on star formation efficiency. Together, they allow astronomers to test whether the impossible galaxies are simply overachievers in the early universe, or if fundamental physics is missing from our models. International Monetary Fund diagnostics in the early universe. The initial mass function, IMF, the distribution of stellar masses at birth, is a cornerstone of astrophysics. Locally, it appears nearly universal, favoring low-mass stars with only a few % forming as massive O or B types. But in the early universe, conditions may have tilted the IMF toward high masses. Evidence is mounting. Webb spectra of Z greater than 8 galaxies show extremely strong nebula emission lines, particularly open bracket O3 close bracket, which are difficult to explain without a surplus of hot, massive stars. The inferred ionizing photon production efficiency, Z ion G subscript ion G, is significantly higher than in nearby galaxies. This hints at an IMF skewed toward 20 to 50 solar mass stars. If true, the implications are huge. Massive stars produce more UV light, drive faster enrichment, and leave behind more black holes, all of which accelerate cosmic evolution. Observationally, Webb's line ratios and continuum slopes provide the constraints, while ALMA's dust and metal content checks the results. By the late 2020s, the IMF debate may finally shift from assumption to measurement. Lyman alpha emission as a reionization probe. Lyman alpha, Li alpha emission at 1216 angstroms is both a beacon and a trap. It is one of the strongest lines produced by star-forming galaxies, but it scatters violently in neutral hydrogen. Thus, its presence or absence in early galaxies is a direct tracer of the ionization state of the intergalactic medium, IgM. Ground-based studies with Keck and VLT already hinted that Li alpha emission declines sharply beyond Z, approximately 6 to 7, consistent with a more neutral universe. Webb's exquisite infrared sensitivity now extends this to higher redshifts, confirming that Lyra is heavily suppressed in many Z greater than 8 systems. But the picture is not uniform. Some galaxies show surprisingly strong Li-alpha even at Z approximately 9 to 10, suggesting they sit inside large ionized bubbles, perhaps carved by clustered neighbors or by hidden quasars. This patchiness matches simulation predictions. Reionization was not a smooth fog lifting, but a patchwork of transparency and opacity. Protoclusters and early environments. Galaxies rarely form in isolation. Already by Z till 7 till 10, Webb har fundet overdense regioner, protoklynger, hvor flere lysende galakser samles. These systems are the ancestors of today's massive clusters, like Virgo or Coma. One striking example is the discovery of a dense grouping of galaxies in Cosmos Webb. Interpreted as a protocluster only 650 million years after the Big Bang, spectroscopic confirmation shows multiple members with strong emission lines, implying synchronized bursts of star formation. The importance of these discoveries is twofold. 1. They show that large-scale structure was assembling rapidly. And 2. They highlight the role of environment in shaping galaxy growth. In dense regions, mergers and inflows may have driven the extreme star formation rates seen in the impossible galaxies. The role of cold flows in feeding galaxies. Simulations suggest that early galaxies were fed not by hot, shock-heated halos, as in the modern universe, but by narrow, cold gas streams, flowing along filaments of the cosmic web. These cold flows delivered pristine hydrogen directly into galactic centers, sustaining rapid star formation. Webb and ALMA provide observational hints. The morphology of high-Z galaxies often appears elongated along filamentary structures. Some ALMA detections of C2 kinematics show inflow signatures rather than outflows. Meanwhile, simulations like FIRE and Illustri's TNG predict exactly such accretion patterns. If confirmed, cold flows would explain how galaxies sustained the star formation rates necessary to reach their observed luminosities so early. They also tie directly into the larger cosmic web, showing that galaxy growth and large-scale structure were inseparable, even in the first billion years. Quenching in the early universe. One surprise from Webb is that even in the reionization epoch, some galaxies appear quenched, their star formation shut down. At Z around 5 to 6, candidates have already been found with red continua and little evidence of ongoing star formation. Quenching mechanisms today include active galactic nucleus feedback, gas exhaustion, or environmental stripping. But in the early universe, quenching so soon after formation is puzzling. Were these galaxies starburst systems that burn through their gas in a few 100 million years? Or did early black holes already begin regulating growth? Future Webb spectroscopy will clarify. If these galaxies host faint AGN signatures, it would prove that feedback operated almost from the start. If not, then rapid starbursts may have simply consumed fuel faster than replenishment. Either way, it shows that the diversity of galaxy life cycles began earlier than anyone predicted. Linking first light to modern galaxies. The galaxies Webb sees at Z approximately 10 to 13 are not just curiosities, they are the ancestors of galaxies today. By tracing their stellar masses, metallicities and environments forward through simulations, astronomers can connect them to descendants at Z equals 0. Some of today's dwarf galaxies may be relics of faint reionization-era systems. Massive spirals like the Milky Way likely grew from the mergers of many such early building blocks. Protoclusters, seen at Z around 7 to 10, became today's giant clusters. This continuity matters because it means Webb's discoveries are not isolated anomalies. They are the missing opening chapters in the biography of every galaxy we see around us. A synthesis, first light as a cosmic laboratory. By the close of Webb's first decade, the birth of galaxies will be one of the best-studied transitions in cosmic history. Already, the data are forcing revisions to star formation physics, efficiencies, IMF, feedback, chemical enrichment, metals and dust appearing faster than expected, black hole seeding, coeval with galaxies not after, large-scale structure, protoclusters and cold flows evident by 500 million years, reionization, patchy, driven by faint galaxies more than quasars. What was once theory is rapidly becoming measurement. The first light is no longer hypothetical. It is observable, quantifiable, and deeply surprising. CEERS and the expanding census of early galaxies. The cosmic evolution. Early Release Science Survey, CEERS, has become one of Webb's most productive windows into the young universe. By pointing NIRCam at a wide patch of sky in the extended Groth strip, astronomers aimed to test how many galaxies existed within the first 500 million years. What emerged stunned the community. Not just one or two candidates, but dozens of luminous galaxies at redshifts greater than 10. Some are bright enough to be seen in relatively short exposures, suggesting that early galaxy formation was far more common than models had predicted. Spectroscopic follow-up confirmed several of these candidates, cementing them as among the most distant galaxies ever observed. SEERS showed more than just the abundance of galaxies. It revealed that these systems were compact, often only a few hundred parsecs across, yet producing stars at furious rates. In terms of density, they outshone modern starburst galaxies by orders of magnitude. Webb's high resolution allows astronomers to study their shapes, showing clumps and irregular structures that may hint at turbulent gas inflows or mergers. These galaxies are not neat spirals or ellipticals, but chaotic building blocks of the future universe. The CEERS dataset continues to expand, with additional fields scheduled, and promises to define the statistical backbone of galaxy formation in the reionization epoch. JDs. Spectroscopy at the frontier. If SEERS is about numbers, the JWST Advanced Deep Extragalactic Survey, JADES, is about depth. This program, combining NIRCam imaging with near-spec spectroscopy, drills into small regions of the sky with extraordinary sensitivity. JDES has confirmed galaxies beyond redshift 13 with precise spectroscopic redshifts, eliminating the lingering doubt that photometric candidates might be misidentified low-redshift interlopers. The JDES spectra are treasure troves of information. They show nebular emission lines like H-beta, open bracket O3, close bracket, and sometimes He2, giving direct measures of star formation rates, metallicities, and ionizing photon production. In one remarkable case, a galaxy only 350 million years old already shows evidence of chemical enrichment, with oxygen levels at several % of solar. Another system at similar redshift exhibits almost no metal lines at all, making it a strong candidate for hosting population 3 stars. The diversity is striking. The early universe was not uniform, but already complex, with some galaxies racing ahead in evolution, while others lagged behind. ALMA follow-ups and the cold universe connection. As Webb reveals the starlight of young galaxies, ALMA provides the counterpoint by tracing their gas and dust. Several SEERS and JDES galaxies have already been targeted with ALMA for C2158 micrometer emission, a key coolant of interstellar gas. In some cases, ALMA detects bright C2 lines, indicating mature interstellar media and organized rotation. In others, C2 is weak or absent, suggesting primitive conditions. The detection of dust continuum in some Z greater than 7 galaxies further complicates the picture. Dust masses of 10 to the power of 6 to 10 to the power of 7 solar masses have been inferred in systems less than 500 million years old, requiring efficient dust formation channels probably in supernova ejecta. These ALMA results pair with Webb's infrared slopes to provide a complete view. Galaxies are not only forming stars, they are cycling gas into dust and metals with surprising speed. This synergy between Webb and ALMA is one of the defining features of modern astrophysics, where multi-wavelength datasets converge to tell a unified story. The puzzle of diversity at early times. One of the most surprising outcomes of Webb's early surveys is the sheer diversity of galaxies in the first billion years. Some are luminous, compact, and metal-rich, resembling miniature starbursts. Others are faint, diffuse, and chemically pristine. A few show signs of quenching, with redder colors and little ongoing star formation. This diversity suggests that galaxy evolution was not a single track, but a branching tree, with some systems racing ahead and others stalling. Environment likely played a role. Galaxies in overdense protoclusters may have evolved faster, fed by cold flows and frequent mergers, while isolated systems grew more slowly. Feedback from black holes may also have been decisive in halting star formation in some cases. The key point is that the early universe was dynamic, with galaxies on many different evolutionary paths, even at the same cosmic time. Webb and the discovery of protodisks. Another revelation from Webb has been the discovery of ordered rotation in galaxies previously thought to be chaotic. NIR-spec integral field unit observations of Z approximately 6 to 7 galaxies show velocity gradients consistent with disk-like rotation. In one case, the data suggest a rotationally supported disk only 700 million years after the Big Bang. This finding challenges the assumption that early galaxies were all turbulent mergers. While many certainly were chaotic, some had already settled into ordered structures remarkably quickly. Combined with ALMA's detection of rotating C2 disks at similar epochs, these observations show that galaxy disks, the fundamental building blocks of spirals like the Milky Way, formed earlier than once believed. The implication is that the processes leading to organized galactic structures were in play almost from the beginning. Quasars and black hole seeds in the Webb era. The coexistence of luminous quasars with young galaxies at high redshift remains one of the deepest puzzles. Webb's infrared sensitivity has identified faint active galactic nuclei embedded in early galaxies, suggesting that black hole growth and galaxy formation were intertwined from the start. Some of these galaxies show broad emission lines, clear signatures of accreting black holes. How such massive black holes formed so early remains unsolved. If they originated from the collapse of population 3 stars, they must have grown at the Eddington limit almost continuously. Alternatively, if they formed via direct collapse, they began already massive but required special conditions to avoid fragmentation. Webb's observations of faint active galactic nuclei, combined with LIGO's census of merging black holes and EHT's imaging of nearby giants, are beginning to connect the dots. By the 2030s, LISA will detect gravitational waves from merging supermassive black holes at high redshift, providing yet another piece of the puzzle. The future of cosmic dawn studies. The progress of just the past 2 years shows that we are entering a golden age of first-light science. Webb has shattered the old boundaries. Sears and JADES have filled the census with confirmed galaxies. ALMA has weighed their gas and dust. And Gaia has anchored the local benchmarks. But the story is far from complete. In the next decade, the Nancy Grace Roman Space Telescope will map vast areas of the sky with Hubble-like resolution in the infrared, providing the statistical power to complement Webb's depth. Euclid is already surveying weak lensing and galaxy clustering, helping to place the first galaxies in the context of the cosmic web. The extremely large telescope will provide diffraction-limited spectra of individual stars in nearby galaxies, refining our models of stellar populations. The SKA will deliver direct maps of reionization in 21 centimeters. matching the galaxies to the hydrogen bubbles they ionized. When all these pieces come together, astronomers will not only describe the first galaxies, they will explain them, tracing their birth, growth, and fate in the context of cosmic evolution. The mystery of first light is transforming from speculation to a detailed, data-rich chapter in the universe's history. The reionization frontier, galaxies versus quasars. For years, astronomers debated whether the reionization of the universe was powered mainly by galaxies or by quasars. The discovery of luminous quasars at Z, approximately 6 to 7, suggested that black holes could pump enormous numbers of ionizing photons into the cosmos. However, the density of quasars drops steeply at higher redshifts, and Webb's surveys of faint galaxies have tipped the balance decisively. It is now clear that galaxies, not quasars, provided the bulk of ionizing photons during reionization. This doesn't mean quasars were irrelevant. In local regions, a single active nucleus could carve ionized bubbles tens of megaparsecs across. Webb's NIR spec has detected signs of faint active galactic nucleus activity in galaxies as early as Z, approximately 8, suggesting that black holes contributed to patchiness in reionization even if they weren't the main drivers. Meanwhile, the continued search for faint, obscured active galactic nuclei in the early universe will test how common such systems really were. Upcoming instruments like the SKA will settle the question definitively. By mapping the size and distribution of neutral hydrogen bubbles, astronomers can measure the relative contribution of galaxies and quasars to reionization. If bubbles correlate tightly with galaxy overdensities, galaxies win. If they appear more scattered, quasars may have played a larger role. The limits of observations and the need for theory. Even with Webb's extraordinary power, there are limits to what can be observed directly. Galaxies at Z approximately 15 may be visible, but beyond that, the first generation of stars and black holes remain elusive. The epoch of population 3 stars, predicted to occur around Z approximately 20 to 30, lies just beyond Webb's reach. Detecting them directly may require a future telescope optimized for even longer infrared wavelengths. For now, theory must fill the gap. Numerical simulations, increasingly detailed thanks to exascale computing, attempt to recreate the conditions under which the first stars formed. These simulations follow the collapse of pristine gas, the ignition of massive stars, and the enrichment of their host halos. By comparing their outputs to Webb's observations of slightly later galaxies, astronomers can constrain the parameters of these invisible epochs. This interplay between observation and theory is a hallmark of modern astrophysics. Webb doesn't just deliver images, it delivers challenges to models. Every unexpected galaxy, every anomalous spectrum, forces theorists to refine their equations and rerun their simulations. In turn, the models predict what Webb should find next, guiding the choice of targets and the design of future missions. Gravitational lensing and the power of cosmic telescopes. One of the most powerful tools for probing first light has been gravitational lensing. Massive galaxy clusters bend spacetime so strongly that they magnify and distort background galaxies. Webb's deep fields often use such clusters as natural telescopes, boosting faint galaxies into detectability. The Frontier Fields program, begun with Hubble and now extended with Webb, has revealed galaxies that would otherwise remain invisible. Some of the highest redshift candidates owe their discovery to lensing magnification. The trade-off is distortion. Galaxies appear stretched into arcs or smeared into multiple images. But by modeling the lensing mass distribution, astronomers can reconstruct their true shapes and brightness. Lensing also enables spectroscopy of fainter galaxies than Webb could otherwise reach. NIR-spec observations of lensed galaxies provide detailed chemical and kinematic information for systems that, unlensed, would be beyond reach. In this way, Nature itself extends Webb's power, making galaxy clusters into cosmic observatories, linking star formation to cosmic backgrounds. Another frontier in first-light science is the connection between early galaxies and the backgrounds that fill the universe today. The cosmic infrared background, CIB, is the integrated glow of all galaxies across cosmic history, while the cosmic X-ray background may contain contributions from early black holes. Webb's measurements of faint galaxies begin to resolve the cosmic infrared background into individual sources, reducing the fraction that remains unexplained. Cross-correlating the CIB with the cosmic microwave background, CMB lensing maps from Planck, provides clues about how galaxies trace large-scale structure. Similarly, future X-ray missions will test whether the X-ray background includes a contribution from the first black holes accreting at high redshift. These connections show how different cosmic messengers, infrared light, X-rays, microwaves, weave into a single narrative of the first billion years. The role of environment in shaping early galaxies. Webb's wide-field programs have begun to show that environment mattered even in the earliest epochs. Some galaxies lived in isolation, forming stars slowly and remaining chemically primitive. Others clustered in proto-groups, where interactions and mergers drove rapid starbursts. Protoclusters at Z, approximately 7 to 10, have already been identified, hosting multiple luminous galaxies in small volumes. These regions are likely the precursors of today's massive galaxy clusters. Their discovery proves that large-scale structure was already emerging only a few 100 million years after the Big Bang. This environmental dependence may explain the diversity seen among early galaxies. In dense regions, inflows and mergers triggered fast growth, while in voids, galaxies remained faint and slow. The seeds of cosmic inequality. Some galaxies destined for greatness, others for obscurity, were planted from the very beginning. Black hole growth in the first billion years. The mystery of how supermassive black holes formed so early remains unsolved. But Webb is providing new clues. NIR-SPEC spectra of faint, active galactic nuclei at Z, approximately 8, suggest that black hole accretion was already underway only 600 million years after the Big Bang. These black holes are not yet the billion solar mass giants seen in quasars, but they are the missing link between stellar remnants and quasars. Theories of black hole growth face severe constraints. If seeds formed from population 3 stars, they had only a few 100 million years to grow by factors of 1 million. Continuous Eddington accretion could achieve this, but only if conditions were extraordinarily favorable. Alternatively, direct collapse models allow black holes to start larger, but require unusual conditions to suppress fragmentation. Future observations with Webb, combined with gravitational wave detections from LISA in the 2030s, will determine which path nature took. For now, the presence of AGN at such early times underscores that black holes were never an afterthought. They were part of the story from the beginning. The chemical fingerprints of first light. Webb's spectroscopy is beginning to reveal the chemical evolution of the cosmos in exquisite detail. By measuring line ratios of oxygen, carbon, and neon, astronomers can trace how galaxies enriched their interstellar media. Some Z, greater than 8 galaxies, already show oxygen abundances at a few percent solar, while others remain nearly pristine. These measurements are not just academic. They constrain the lifetimes and masses of the first stars, the efficiency of supernova enrichment, and the rate at which metals mixed into the intergalactic medium. In some cases, odd abundance patterns suggest unusual nucleosynthesis, possibly from pair instability supernovae. If confirmed, these would be the first direct chemical fingerprints of population 3 stars. By combining Webb's spectra with ALMA's far-infrared lines, Astronomers can reconstruct the chemical story of the first galaxies. When metals appeared, how they spread, and how quickly dust followed. This chemical archaeology turns galaxies into laboratories of stellar physics at cosmic dawn. The legacy of Hubble and the leap of Webb. It is worth remembering how recent these breakthroughs are. Only a decade ago, Hubble's deepest fields pushed to Z, approximately 8 to 10 with great effort, and most candidates lacked spectroscopic confirmation. The first glimpses of galaxies at Z greater than 10 were tantalizing, but uncertain. Today, with Webb, such galaxies are routine. Spectroscopic redshifts beyond Z, approximately 12, are not press releases, but standard results. The leap is staggering. Hubble opened the window on high redshift galaxies, but Webb has thrown the window wide. Where Hubble saw shadows, Webb sees detail, emission lines, morphologies, dust signatures. The difference is not incremental but transformative. The history of the universe's first billion years is being rewritten before our eyes. A universe stranger than expected. The first chapter of Webb's discoveries is a reminder that the cosmos is often stranger than theory predicts. Galaxies formed earlier, grew faster, and enriched themselves more quickly than models allowed. Dust appeared sooner. Black holes grew faster, and reionization was patchier. Far from closing questions, Webb has opened new ones. This is not failure, but progress. Science advances when predictions are broken. Each impossible galaxy is an invitation to refine our understanding of dark matter, star formation, feedback, and cosmic evolution. The first light is not just illumination, it is disruption, forcing us to rethink what we thought we knew. The first light. It is clear that the story of first light is not finished. Webb's next decade will deepen and broaden the census. ALMA will continue to weigh gas and dust. Gaia will refine the local anchor points, and SKA will map reionization directly. By the 2030s, we may know not just when galaxies formed, but exactly how and why some raced ahead while others lagged. For now, the lesson is awe. The universe's first billion years were not a quiet prelude, but a furious symphony of star formation, black hole growth, and chemical alchemy. From the first stars to the first galaxies, from darkness to light. The cosmos revealed itself with breathtaking speed. The journey of discovery is only beginning. The first light is our prologue, and the chapters ahead. Black holes, dark matter, cosmic webs, alien oceans, promise to be just as surprising.